I wanted to add something because we were talking about online optimization. That's what I was discussing with Andrea. So the experiment that our ETH student is running here is exactly feedback optimization on the power distribution grid, right? And it works very, very well. So it's something very far from what practitioners in distribution grid will do. Very far, like right now they basically have no control of the power distribution grid. We will see something about that today. But if, just by experimenting here, they have a nice test bed, you can write your code, you can try it here, and it works. And the math behind that is basically what Andreas presented. So the gap is not, continuing what Spiros was saying, the gap is not so large. Sometimes the gap is about understanding the problem better, and then the solution you want to apply is actually not so surprising. I mean, at the end, what they are actually testing is a controller that can be embedded in the microprocessor on the power converter. It's not something that requires, something people in this industry have not been exposed to before. Okay, so this was just a comment. So today, what I'm going to talk about today is something a bit different. It's about data-driven control for power distribution grids. So we'll go through a bit of introduction of what distribution grids are, what is data-driven control, in the sense that what is chance constraint optimization, how do you take measurements into account. It's going to take about 3 hours in total, but we'll take a break. I suggest we take a break at the end of this first part, or maybe we are able to cover this one, but not more than 1 hour from now, okay, if it's fine for you. These are the 3 parts we're going to cover. The first part, so first of all, you notice there is an interleaving of theory, a presentation, and exercises. So you will have to listen to me talking for a little bit, and then you'll have to do an exercise number 1. And then I'll talk a little bit more about scenario approach, chance constraint, how to represent them mathematically, and then another exercise. The second part is a bit shorter. And the third part is long again, and it's a bit more theory about how to incorporate measurements in this chance constraint problem, and the final exercise. And the last part here is something relatively recent. It's something we've been working on, and this is the paper that has been shared to you on the website. The part before is kind of a setup for this solution, but it has its value per se, right? It's a number of methods you might find useful. Okay, so for the exercises, the way I set it up is to create these CodeOcean capsules. So basically, if you have a login on CodeOcean now, you can import the code that I've prepared, and then from there, you can actually solve the exercises. So write down the part of code that you need to write, which is not going to be too long. The main advantage is that in these capsules, it's like Docker, if some of you have used it before, everything is already pre-installed and everything is there. So you click a button and you see the results. The main disadvantage is that it's a little bit less flexible for trial and error things. You need to write your code properly because you don't want to push the button and then see that you missed a semicolon somewhere. You need to write your code properly. But I think this is more an incentive than a drawback, right? So you'll see. If you want to copy the code and use your MATLAB installation, that's also fine, but then you need to make sure you have all the toolboxes. Okay, let's start. So notation, I'm sure, I wasn't 100% sure about the notation used by others, but I try to stick to this notation in this deck of slides. Capital letters are typically matrices. I think I'm quite consistent with this one. Vectors are lowercase letters. If I need if I want to denote a slightly different vector or maybe a vector from a sequence, then I put something on the superscript, right? The G, the index I, or so on. On the contrary, if I'm referring to a scalar, so one of the elements of the vector, then it will be a subscript. Okay. To reduce confusion, if I write 0, it's a scalar 0. If I write 0 with the double bars, it's the vector of 0. If I write 1, it's a scalar 1. If I write 1 with the double bar, it's a vector of 1s. And then I'll use only 3 concepts, which you should have been exposed to already, which is probability, expectations, and covariance of a vector, of a random variable, a multidimensional random variable. If the random variable has dimension n, the covariance is a matrix n times n. The diagonal are the variances of the elements of the vector, and so on. Okay. Just one or two slides about distribution grids to make sure we are all on the same page, including people that don't have a power system background. For those that have a power system background, just be patient for a minute. So the grid is organized, the power system is organized in a very hierarchical way, almost in a fractal way, if you want, in the sense that there is a backbone of the grid, which is the transmission grid. This is the high voltage one. It's the one that goes on the power lines, which are on these lattice towers. It's where the traditional power generation is connected. Okay, big power plants, nuclear plants, coal plants. Then from the transmission grids, there are substations where the sub-transmission grid lives, which is the grid which is at a slightly lower level, medium voltage level, and this is the quite smaller in size, but goes down to the neighborhoods, to the cities, and so on. And the end part is the distribution grid, which is the last part after the last substation, is the one that brings power to your home, right? Not really to your home like to the outlet in your home, but like closer to your group of houses or something like that. And this is typically low voltage or medium low voltage. It's a radial network, so there are no loops. It's just reaching all the houses with the minimum amount of wires. And it's where all the buildings are connected, right? This is the big picture. And now this is, let me see if it changes smoothly. This is the future picture, how it's currently predicted by most of the people working here for sure, and also in other places, is that we will have something different in this in the way this is operated. So instead of a power flow from the transmission grids to the buildings, now we have renewable energy sources in the distribution grid. We have a different kind of loads, for example, electric mobility in the distribution grids. And this means that the power flow is sometimes from the transmission grids to the distribution grid, sometimes actually it's reversed, and sometimes it goes from a distribution grid to another distribution grid. It's much less predictable, right? It used to be something like a one-directional flow. Now it's a bit more complicated. And on top of that, we have some features which are a bit tricky to manage. One is that the renewable energy sources are quite good to be predicted on a medium long-term horizon. Like you can have weather forecasts for tomorrow, but it's quite difficult to predict your wind power in the next 1 hour, right? It might drop, it might rise, and you don't really know. Moreover, this uncertainty is not the nice IID uncertainty that you see in many textbooks. If you have 2 wind farms or if you have 2 solar panels, you cannot assume that because they are 2, the variance of their fluctuation is going to be less than 1 because they actually see the same sun, right? And the same wind. So the correlation of this uncertainty doesn't really decrease when you have multiple units. For electric mobility, I'll show you some numbers in the next slides. The problem of electric mobility is that it's a very high demand, both in terms of peak power and total energy. And it's not clear if the size of this new kind of demand can be just managed by allowing them to be flexible, because being flexible it could be an advantage for the operation of the grid, but could also create more challenges. And they have some very weird spatial temporal patterns, like everybody going home at some point during the day, or connecting the congestion on the traffic network to congestion on the electricity network. Like if there is traffic, then the delay, the peak of power is delayed because people, they're taking longer to get home. And I wanted to include some numbers. Now these are a little bit old. These are from 5 years ago, but this gives an idea of what is the kind of problem you are going to see in distribution grids. So this is the total power generation in Germany in summer 2014, one specific day. It's a lot of wind, a lot of solar, a little bit of hydro, and a little bit of biomass, and only a quarter of the total generation was coming from traditional power plants. Now, this would be fine if all this generation happened in the transmission grid. The problem is that if you see where this renewable generation is installed, solar is installed almost for 100% in the distribution grid. So anything to the right of the line is in the distribution grid, anything to the left is transmission. Wind as well, right? Some wind farms are connected to the transmission grid because they are offshore or in a big open spaces, but some half of it is actually connected to the distribution grids, maybe to the middle voltage, right? And the same for hydro and biomass, depending on the country, because hydro may mean like big, huge installations in the mountains, but maybe micro hydro as well. And the last one that I wanted to show in terms of numbers here is energy consumption by sector in 2010. So also this one is a little bit old, but gives the idea. This is energy, not electricity, energy consumption of 3 different sectors: buildings, industry, and transportation. And if it's on the right of the line here, it means it's served by electricity. It's on the left, it means it's served by primary fuel, like gasoline. Right? And you can see that for buildings, yes, we are already delivering electricity to buildings. We know how to do that. For industry as well, more or less. But for transportation, the entire energy demand in transportation is served by the gas you put in your car, or if it's cars, but also for most of the other transportation. This slice thin red line here that you see, it's trains. And that's the only thing that is served by electricity, right? So if you see this project where, I don't know, 50% of the transportation of the mobility is going to be electric in 10 years or something like that, you have to imagine that half of these will move to the electricity part and will have to be served together with buildings and a bit of industry. Okay, and then to conclude this introduction, this is what I define by congestion in the power distribution grid. Power distribution grids, because of these reasons, may reach their power transfer capacity that was designed for a much smaller loads and for no generation. And the limit, the transfer capacity, is determined by the limit of the current that a power line can carry, by the rating of the power transformers that connect the distribution grid to the higher voltage grids, and by voltage bounds, because we will see today power flow affects the voltage and the voltage needs to be bounded. Okay, is this part clear? Is there anything that was incredibly surprising? Not really. Okay. Now, this is the test grid we're going to use as an example, and also in the exercise is one of the standard test feeders from IEEE. It's very old. Like all these test feeders come from the 90s, so they have no generation, so we had to add a couple of them. We added 2 generators here. No matter what they really mean, these are 2 generators in the distribution grid. The distribution grid is this thick black tree, and it's connected to the substation, to the rest of the grid in this point here. Okay? And so the 2 generators are one in the middle, more or less. One at the extreme is the longest, is the farthest, if the point which is farther away from the point of common coupling. And all these dots here are loads. I've considered all the loads in these radial parts here lumped on the backbone of the grid for simplicity. So if you see the test bed later in the exercise, it has actually 55 nodes, not 123. Okay, so what can we do on a distribution grid like this one, where we can actuate the grid, not as much as we can actuate the power transmission grid. In power transmission grid, if the power system operator wants a given power flow in the network, he'll just have to dispatch commands to the generators, and that would happen, right? In the distribution grid, you don't really have control of any of these dots here. The only thing you can do, you have, for example, you can curtail generation. So, for example, you can tell this generator, don't produce more than 3 megawatts because this is too much for the grid to transfer. You can shed loads, so you can just, not all the loads, but some loads can be disconnected if that's requested by the distribution system operator. You can control reactive power, so the injection of reactive power by some of these devices. And you can do quite a bit at the point of connection here. For example, you can change the ratio of the transformer there. But you see, these are a very limited amount of actuation that points that you have on the system. Most of the other things are actually not under your control. Loads will connect and disconnect when they please, and so on. And in terms of sensing, this is even a worse problem. These networks are almost unmonitored right now. So there's no measurement in these networks. The only measurement is a very limited number of real-time sensors, typically at the substation. Like I know how much power is flowing in, and not even at all substations right now. Sometimes people are suggesting to put a few very precise measurements in the grid, like I put, I don't know, 1 voltage measurement at the end of the grid here because I want to monitor that. But it would be like one sensor. Very different from the transmission grid where you have your nice monitors in the control room and you have the state estimation for the entire system. And then there is this smart metering thing, like you are collecting metering data from the loads, typically for billing purposes, but this is delayed. This is collected sometimes once per hour, sometimes one per day. Sometimes it's just sitting there until a guy goes there and reads the number and writes it down, right? Okay, so what are the goals? The goal is to operate this grid, also to decide how to actuate the grid so that the operational constraints are satisfied, voltages are fine, currents are fine, and so on. If you need to decide what kind of actuation to apply, then you would like to minimize the curtailment of generation and the shedding of loads, because that's very expensive. For curtailment, well, it's easy you just look at the price of energy and you're just curtailing free energy from a renewable source. That's not the ideal case. And for shedding, it's typically distribution system operator have this just table that says if you shed 1 megawatt hour, then you have to pay 80 euros. Okay, this kind of thing. So it's a true monetary cost. And then if these are fine, then you also may think about reducing losses on the lines, or you may want to provide some services to the rest of the grid. For example, for frequency regulation, I want to decrease my total consumption. I want to increase my total consumption, so on. Today, we're going to focus on what you see in bold here. The actuation that we are going to consider is only generation curtailment. The sensing is real-time and delayed data. And the goal is to satisfy operational constraints while minimizing curtailment. But everything else can be incorporated. Okay, so a bit of power flow equations. It's only one slide on power flow equation, but it's just to introduce the notation mostly. This is just a very schematic representation of a grid similar to the one you've seen before. What I'm assuming is that there is one node where the voltage, little v is the voltage magnitude, theta is the angle. The voltage is 1, because that's just the per unit value of the voltage at the substation. All the other nodes are PQ nodes. By PQ nodes, I mean that on these other nodes here, there is either a generator or there is a load, which is either injecting or requiring a given and fixed amount of active and reactive power. Okay? And the active power, I write it as P, reactive power as Q. And then, of course, with this information, you can apply Ohm's law and Kirchhoff laws and solve the rest. The current would be a function. Current on a node would have to sum to 0 for conservation of current. Complex power is the inner product between voltage and current, a complex conjugate of the current. You put this thing together, and you have a matricial form of the power flow equations. So this is a nonlinear set of equations, which if I give you the power demands of the power generation at the different nodes, and if you're able to solve this one, then you get U, which is the voltage of the grid, which is basically the state of the grid, magnitude and angles. And the parameters of the grid, like the line length, the line impedance, they appear in this Y, capital Y here, which is the bus admittance matrix. Okay? We will not talk a lot about how to solve these equations here, actually not at all. But this is all you need to know about power flow equations to follow the rest. Okay? It's nonlinear. There are results, in case you're interested, showing that solving these equations for distribution grids, which are radial, it's a bit easier than solving them for transmission grids. But it's not apparent if you just look at them, no matter how long. Okay, so as I said, this is a set of nonlinear equations. So if X is the state of the grid, I put just together the voltage, the angles, the active and reactive power injections. Then these equations here, this is a set of nonlinear equations that define a manifold, so a subset of the entire state space, where these equations are satisfied, where this h of x is equal to 0. So this is just a representation on just a few variables in a 2-bus case, the simplest case. All points on this grid here are points which are solution of the power flow equations. Okay? You can actually show, we showed in a old paper now, that this is a regular manifold in the sense that it has dimension 2n everywhere. It doesn't do strange things like twirling around or anything too bad. It's just a nice set. It's a nonlinear one. And for today, we need linear models. We need a linear model because we want the problem to be convex. Otherwise, it gets much more complicated to solve. We want to have a compact representation that comes from the linearity of the model, you will see later. And we want to do decision in real time, which requires the math and the computation to be simple. And this works better for linear models. So from this nonlinear model, we want a linear model and a quite accurate one. And so to do that, we use exactly this mathematical result to show that this is actually a submanifold, a regular submanifold, because one of the consequences is that in a submanifold, you can always attach a tangent plane. To any point of a submanifold, there is a tangent plane of dimension 2n that you can attach. And that's what we do here. So this is how we do our linearization. We take any operating point of this power system, of the grid that you have. You can measure it, for example. You know the nonlinear power flow equations, and you know that you can attach a tangent plane to this operating point, so a plane which is tangent to these nonlinear power flow equations. If you see it like here, it's basically a Taylor expansion of the power flow equations, but on the operating point. Okay, I think this is useful tool to know. Because it's the model that you get is this model here. So instead of this h of x is equal to 0, what you get is a times x minus your operating point is equal to 0. So you have a linear model, right? And what's nice of this model is that it's implicit. So there are no inputs and outputs here. I'm not telling you what you are controlling, what you're measuring. This is just telling you this is the space of points which are consistent with the power flow equations in first order approximation. And this is not a disadvantage, you will see later. The matrix A turns out to be sparse. So if you have a very large network, this is sparse, this is very fast to manipulate if you have the proper numerical routines. And it's structure preserving, which means that the elements of this matrix A depend on the parameters of the grid in a local manner. Like if you change one line in your network, you will only have to change a limited number of elements in this matrix A. If you want to see how to construct this matrix A, there is a paper a very short paper, to be honest, where this is explained with exactly the mathematical formula that you need to use to construct this linearization. And many of you probably have seen already linearization of the power flow equations, like the DC power flow, the Lin-Dis flow, other things. Like we're not the first one to do linearization of the power flow equations, but these are actually special cases of this one. So if you, depending on where you put your linearization point and other assumptions you can make, you get all the other linearization that you have seen probably in the literature. So if you need to write code where you need to use a linear model of the grid, I actually recommend, or you may want to use a method for linearizing, which does not depend on assumptions that sometimes are verified, sometimes are not. This is the best linear approximant by definition, is the tangent plane to that point. Okay, so it's a trick to keep in mind. The exercise today will not involve you computing this one. It's done for you by a script, a function I provide. Okay, so I told you before that we are looking at the problem of satisfying constraints with generation curtailment. So for the lecture today, it's a bit more convenient to use an input-output linear model. So we take this this implicit map that I showed you before, A times x minus x star is equal to 0. And we would actually want a map which is explicit, like it tells you the voltage of the grid is going to be this function of active and reactive power injections. Okay, it's exactly the same in the sense that if you take this expression and you take the expression of A and you solve it, it gives you 0. And if you take this one and you manipulate a little bit, you get this expression, right? So there's no advantage in doing that. So we are going to use an explicit map like this one today, also for the exercises, just because it's much easier to interpret than the other one. What you lose here is that this is not sparse anymore, so numerically speaking, it's not as efficient. That's why I wanted to mention the other model as well. Notice that this is very reasonable. This is saying that the voltage at the bus is 1 plus something which is linear in the active and reactive power injections. So if you don't have active and reactive power injection, then the voltage is 1 everywhere. This is very reasonable, right? If you don't have any power flow, then the voltage is the same as the substation. And also remember that these P and Q are the injected reactive power at every bus, which is the difference between what's the power demand and the power injection in that bus. Okay? So what is this? Now, the only thing which is left to discuss here is actually this coefficient R and X. Let's focus on R only for today. What is R? R is what most power system practitioners would call like a sensitivity matrix, because it's telling you what is the linear dependence between power injections and the voltage magnitude. It's the first order approximation of this effect, right? So it's a matrix. An element in position ij is telling you the effect of voltage of power injection pj on the voltage vi. Okay, so it has an interpretation, although if you apply the numerical routine, just it comes from the linearization of the power flow equation, but it of course has an interpretation as a sensitivity term. In the case that we are considering, where the network is, there is only one slack bus, which is the point where it's connected to the transmission grid, and the rest is all a radial network of PQ buses, then this matrix R is actually, can be inspected and constructed very easily. Numerically, you can take the bus admittance matrix, you remember the Y at the beginning, invert it, and with some minor manipulation, you get the R. Elements have an interpretation, so what I mean here in this expression so if I have ij is, for example, I don't know, this node and this other node here, then Rij can be interpreted easily as the first order approximation of the effect of the power injection here on the voltage Vi. But you can also, if you just, and that's of course, it's valid if you can observe this first order effect. But if you only have the parameter of the grid, this is also the resistance of the path, of the intersection of the two paths. So the intersection of this path here. Any colorblind? And this path here, the intersection is this part here. Rij is the resistance of this P of this intersection. Okay? Just you'd never use it when you write your code, but when you inspect your code or you try to understand why something is happening, this is sometimes useful. Yeah, 0 is sub. And then, so if you need interpretation from power system, is this one. If you need how to construct it, is this one. If you need the mathematical property, I need to tell you also that R, all the elements of R are positive, but R is also positive definite as a matrix. And last important point, if you don't own a network at all, but you have data, you can just estimate R because you know that this is a first order approximation. You just collect a lot of power flows, a lot of voltages, and you see what is the relation between them. Okay, and so for the exercises only, we will leave a few of simplifications here. The simplification is basically that there is no reactive power flowing in the grid because we assume that the loads are compensated and generators have unit power factors, so there is no reactive power, so we just drop the Q. Remember, it was 1 plus RP plus XQ. We drop the XQ. It's literally only for simplicity of the exercises you will have to solve. So the power flow equation that we have is now voltage is 1 plus RP, which tells you if I inject active power, then it will raise the voltage of the grid. And P is the difference between what's generated and what is the power demand. If you put them together, you have this model here, which is also here, which is basically the one you will use in the exercise. The voltage is this function V of generation and demand. It's 1 plus matrix RG times the generation, matrix RD, R times the demand. The matrix RG are just the columns of R corresponding to the buses where you have generation. Okay? Because you don't have generation everywhere. So G is a vector of small dimension, like you have a network of 55 nodes, but you only have 2 generators. So this is dimension 2, but this is the power demand as dimension as the number of loads connected to the grid. This is very large. Okay? And this is only for the exercise. You could remove these last 4 slides, use the implicit math from the beginning, and the math will be perfectly fine. As we're going to use this one later, is it clear? Do you have any question on the model we're going to use? So this is a matrix R is, let's say N is the number of buses. This is N times N. And if you have generators only in some buses, I don't know, bus 3, 10, and 11, then if you take this column, and this column, you put them together in RG, which is N times 3, okay? So RG is exactly the same. There's no more information in RG than in R. It's just columns of R. Okay? Yeah? It's minus. Good point. If you see typos, because I'll update them later, it's minus RD. Thank you. From here, right? Both here and here, this is a minus. And we will refer to this one as V of GD in the rest of the presentation, so you will not see this typo anymore. Okay. Now, this is the problem we're going to consider today. Given all this introduction, this is the problem we want to solve. As I told you, we focus only one problem today, at least in this lecture. It's about how to curtail generation to make sure the voltage is fine. No over voltage is reached. So this is the simplest problem. As I said, you can make it more complicated, but this is good enough for what I'm presenting today. You want to maximize generation, which means minimize curtailment, subject to voltages. Remember, V of GD is the voltage at all buses, being less than some Vmax. Okay? Vmax is, I don't know, 1.02. It's the limit on the power on the voltage that you would like to maintain across the network. You don't want the voltage to be above Vmax. The voltage is a function of generation and demand, and you want to maximize generation so that curtailment is minimized. Okay? as a distribution system operator, this is usually the only information, the real problem you have to solve, because you might have a communication channel to the generators. So you can send them a signal and say, don't inject more than this. But that's it. You don't have control on anything else, and you don't have a lot of other measurements. Now, if you look at this problem, it's not really well defined, right? There is something missing here. So here, this is an optimization problem where there is a parameter d that I just told you you don't know. So how do we want to solve this problem? Well, you have seen already some of these solutions, but you will compare some of them numerically in the first exercise. One may want to solve it for the worst case d, right? I have all the possible power demands I can observe on my grid. I want the voltage to be below Vmax, okay? I cannot measure D, so that's a safe bet. But another person might say, okay, I want the voltage, I want to set my generation so that the voltage is fine, is below Vmax for a typical D. I know it's Thursday morning or Wednesday morning, the demand is typically this one. I want the voltage to be fine if the demand is typical. Or I want that to be true for an average value of D over maybe some observation, or for most distribution. Maybe I am fine if sometimes the voltage is not okay, but for most possible demands, this should be satisfied. And there are two kinds of uncertainty here, was mentioned even before in one of the answers to your questions. We don't know these uncertainty in two different ways, which are subtle but are different. The first one is that we don't know D because we cannot measure D, right? And so we don't measure D because it's not part of our sensors. So we don't know the power demands. We have to do something about this kind of uncertainty. And the other kind of uncertainty is the uncertainty in the distribution of D, right? So maybe we don't know D, but we know very well that it needs to belong to a very limited set of possible options. Like you have one load, it could be on or off, right? In this case, you still don't know D, but you know the distribution of D. You know that 50% of the time it's on. And you can only take two values, 0 or capital D, okay? But now, these are two different concepts. You might also don't know D, but know the distribution of D, and not know the distribution of D. You can also know the distribution very well. Sorry, that's the example I gave. You can also know the realization. Suppose you can measure it, but you maybe don't know where is it coming from. You don't know the distribution behind that, okay? And so we will see basically a mathematical interpretation of these 4 points, one after the other one. You have seen it already, but today you'll have also to compute these values. So the first one is the robust optimization one. Typically, just to avoid any misunderstanding, when people, at least from control, but mostly from optimization, say robust, they mean extremely robust. They mean worst case. Robust against all possible disturbances, not just robust in the sense better than solving something not robustly. It's the worst case analysis. It's maximization of my generation subject to the voltage being fine, so being below Vmax for all possible demands, belonging to some calligraphic D here, which is really the set of all possible power demands. Okay? You will have to do it in the exercise, but I already have here a couple of comments that I want you to keep in mind in the exercise. The first one is that solving this problem might be trivial, numerically speaking, or might be incredibly complicated, just depending on what shape has this set D, right? If this D is a very high-dimensional cluster of points, then actually this robust optimization might become very simple. If this is a box, then it's typically easier. So depending on what is the set D, this numerical problem can be difficult or simple. The second point is that if you are into game theory interpretations for this thing, this is basically a game. This can be formalized as a problem where you are player one deciding the the generation of your generators, and there is player 2, which is your adversarial in some sense, which picks the demand in a way to, to violate the voltage constraints. It's just an interpretation, but if you are interested, if you do that, it allows you to use tools from game theory for this problem. It might be a fun exercise. Then very often, and this is actually what we are going to do in the exercise, D comes from first principles. Like, you know that power demands are always positive or 0, right? Because it's not that a load starts injecting power at some point. So D is a very conservative approximation, but you could say, okay, D is going to be the interval 0 infinity times 0 infinity times 0 infinity, right? So the quadrant, the orthant, the positive orthant of dimension n. That's, well, one possible set D that you could use. If you have data, you can estimate D, but a warning, if it's high dimensional data, this is very difficult to estimate. Think about having, you want to, in one dimension, if I give you 2 points or a few points, you know exactly, it's very easy, to know where is the largest segment that contains, the smallest segment that contains the points. If it's in a plane, it gets a bit more difficult. If you are trying to estimate a cube, then you need a bit more points to understand where are the vertices. If it's higher dimensional, then it's very difficult to give a good estimate of this set. And of course, this is usually very conservative. You get some worst cases, which are very infrequent. Okay? Is this clear? You will have to do it, so it needs to be clear. Okay, second formulation is the one corresponding to what I said, like, oh, it needs to be, constraints needs to be satisfied for a typical D, or for the average demand. And this is what we do here. We say, okay, we want to maximize generation such that the expected voltage is less than the Vmax. Now, this is the nice thing about this one compared to robust, that this is incredibly easy to compute because the model is linear, the expectation can come in the model. This is basically checking that the voltage for the expected demand, for the average of demands, is feasible, right? It's a one line. You are left with a linear program of dimension number of generators with n constraints. Okay, it's trivial. Another good thing about this one is that the expected value of D, it's very easy to estimate. You don't need to do distributionally robust things to compute the expectation of samples, right? You have all the demand in the last 2 years. From your smart meters, you take the expectations and you put it in your cost function, in your constraints. Okay? And the last point is a negative, is a drawback of this approach, is that this is really not what a practitioner would like to hear. I mean, saying that on expectation the voltage, the constraint is not violated, it doesn't literally mean anything. In the sense that you can think about this one, it's not part of the exercise. You can easily construct a distribution so that the expectation is fine, but with 99% of the cases, the voltage limit is violated. Just take power demands, which are always very high, and sometimes are 0, right? The expectation is 0, move the expectation down a little bit. So you would say, oh, then 99% of the power demand is my expectation. I'll put there the limit, meaning that almost everywhere, almost always, I'm violating the constraint, right? I'm only not violating the constraint at 1% of the cases where the demand is 0. Okay, so you can easily construct distributions where enforcing something in expectation means literally nothing for typical operation of the system. And then this is the last one that you have seen before, and this is much more reasonable. This is the chance constraint, is the probability of having a voltage violation that needs to be sufficiently small. So the probability of satisfying the constraint needs to be sufficiently large. Okay, this is better than saying the average. This is saying that it's really like on how often does it happen that the constraint is violated. It is this practical interpretation. Unfortunately, it's typically very hard to compute exactly. So if you give a distribution, to know what is 95% of the cases, of the extreme cases, so what is the tail of the distribution, is typically unknown in a closed form for most distributions, right? Except for the uniform distribution or the Gaussian distribution, right? So if we knew that D is Gaussian distributed, then we would know how to compute this one exactly, for example. And this is something that I wanted to try. So suppose the following. Suppose that you don't know the power demand. I will give you some data from real power demand, but you don't know the distribution, and you're too lazy to try to identify the distribution. You say, it's probably Gaussian, right? It's sum of 55 power demands. When you sum n random variables, with n being very large, eventually you get something which looks like a Gaussian distribution. You think you're fine. This is a Gaussian distribution. For Gaussian distribution, you know how to compute the average. You know how to compute the standard deviation, right? And for Gaussian distribution, you know that the probability of violating, of being in the tail is known. There is a table you can get from MATLAB, okay? So what you could do here is to say, you know, I want this probability being larger than 95%, so I want to exclude the tail of area 0.05. And if you see from these tables, this is 1.65 of the standard deviation, right? If you take a Gaussian, you are outside of plus minus 1.65 only 5% of the cases, okay? You can compute the expectation and variance from the data and try to apply this one, and you tell me what happens. This is very tempting because you know, Gaussian, the approximation of Gaussian distribution is done in the vast majority of stochastic optimization problems, right? Especially in control. So I want you to see if this works or not. Okay, so this is the first exercise. I set it up this way. Let's say if it works. So if you have an account in CodeOcean, I will show you, I move there on my computer and show you how to do it, so you don't need to start now. But if you take this account, in the account, you can basically take my repository and copy it into the CodeOcean capsule, meaning that with a minor tweak I will have to show, you can press a button and see the result. It's a repository where you have a lot of functions which are useful and are self-explanatory. If you look at them, you should understand what they do. And then with those functions, you will have to write a piece of code, a script, to verify the accuracy of the linearized model. You can use a function. You just have to plot it and see what happens. To use this historical data that I provided to check what is a typical distribution of voltages, how many times do you have an overvoltage. Then you consider only one generator. I made things very simple. Is one generator about bus 20, okay? Because the original network doesn't have generators, you have to add one generator. Consider a limit of 2% of overvoltage and a chance constraint desired limit of 95% probability. And then I want you to compute the optimal curtailment, so the maximum generation of bus 20 to ensure voltage satisfaction in the worst case, in expectations, and in chance constraint using this Gaussianity assumption. Assume the voltage, the data are Gaussian, and compute the 95% percentile of the Gaussian distribution. And then you take these three numbers, you pretend that the generator is injecting those three numbers, and you see what is the resulting voltage distribution. And you know, there's a spoiler here. You have to tell me why it doesn't work. So let me show you very quickly how this thing works. Ooh. Okay, so you copy this link here. Okay, and you go to your CodeOcean page. No, you don't have permission to do what? Yeah, no, on your page, on your CodeOcean login. No, don't do anything yet. Go to your login page. On the slides. Yeah, that's why I'm showing you, because the one on the slides is not working. So you just go to your own page, which will not have my face and the other things. It's your page. And you click on import Git repository. You paste the Git repository, and you press import. Okay, because okay. Now I see the problem. Okay, the link, either you copy this one by hand. I think you have a different version. Yeah, I know now. Okay, I think this is not a play. Okay, sorry. So it's github.com/SaverioB/ It's not the link in the slides, sorry. Okay, now I understand the confusion. Okay, and then you copy it in here. And you import it. Then stop when you are at this point, that I have to tell you one more thing to do.
So this is a solution to when you don't have MATLAB, you can run.
Well, this is a solution. Is a solution to create some code which is very reproducible. Like if you publish a paper and you have some code in your paper and you put it in here, then any reader can just press a button and see the result. And in 5 years, where MATLAB would have a different version and other things will be different, they will be able to run it anytime.
So it's like Docker, but
it's Docker, but it's online.
MATLAB.
Yeah.
It has
It has
MATLAB.
MATLAB. It has some test case. Yeah.
That's what the most. I mean,
yeah, sure. I mean, they have a license to allow MATLAB for.
Great.
Okay. Did you get to this point? Okay. Oh, we need a link yet? Sorry. This one. github.com. Oh. Okay. It's now there on the whiteboard. So when you are here, the only thing that I couldn't make automatic, not exactly sure why, is that the way this thing works is the following. Now, each of you has this computational capsule, that's how I call it, meaning that you have an environment. If you click on environment here, this is MATLAB 2017 with some packages that you can install, any packages from the Linux distribution, because this is on Ubuntu 16.04, and other things. Among the other things is other things you can install and that you might need for the exercise. So if you click on edit post-install script, it will create an empty script, right? Which is things you need for this exercise. Now you go to post install copy me, you copy everything, and you replace the content of post install with that part, and then you save. Okay? Unfortunately, this. So you take everything, so you go to environment, you edit the post install script down here. This creates a file which is called post install. And then you take everything in post install copy me and you put it in post install. Unfortunately, just renaming it doesn't work because of permissions, and there's no way to fix it here, and I couldn't get assistance on that. Okay?
That's all your dependencies.
Yes. So what this post install thing will do is to install MATLAB, YALMIP, everything. Okay? Now, let me show you very quickly how this works. There is a folder called code, and then when we are done with this one, we can take a break. There is a folder called code where I prepared a number of functions which you will find useful. And for almost all these functions, there is also a test, right? So if you have a function called generators, there's a test at generators that shows you exactly how to use that function, okay? And then there are some two scripts which are actually very useful for the first exercise, and you will see, okay? What you need to do to run any of these scripts is to select one of them. For example, test environment, which is, I guess, the very basic one, is testing that everything has been installed. You click here and you say, this is the one that I want to run. Okay? And then you click on reproducible run, and it will run it. Okay? The first time you run it, it takes a bit longer because it's installing all these packages, and then it's much faster. So give it a minute, maybe, or something. No, it's fine. You don't have to commit.
Looking for a suitable machine to run your code. So looking for a suitable machine. It's saying looking for a suitable machine.
Oh, okay. It's just because it's.
Maybe it's
Okay. It seems like it's just the too many requests at the moment, or it's not?
yes, maybe. Somebody's running or
Okay, now it's running. Yeah.
Probably it's frozen if you run.
No, it's
It's like you because it's the cloud.
yeah, it's two people running at the same time, I guess, from maybe this IP address probably, and but then when people will be desynchronized, it will be fine. They're running already, and it will start soon.
Okay, so can you put back the slides of the exercise?
Yes. So of course, excuse me, one thing you'll have to do in the folder called code, you create your exercise1.m. You have a folder called code, and in that one you create something like exercise1.m, and that's where you put your code, and that's the one you set to run, right? All the other tests and everything is for you to see how different things are used and to give you an idea of how to use all the scripts I've prepared. If you have any question, just ask me. Don't be completely lost in those scripts. But it should give you an idea of how to use all the functions I've prepared. But then write your code in here, and this is the one you keep running to see the results you want. Okay? Maybe before the break, we wait until everybody is finished, and then I can help the one that I haven't managed. Okay.
The coffee break is already in the tent.
In the
so
tent,
you
okay.
can already announce.
Okay, okay. But Spiros told me you want a group photo first.
Yes,
Okay.
Yeah,
So first a group photo. Okay. It's still looking for a.
Thing. What does this say?
Try HTTP in front. Maybe it's the only problem. I cannot imagine it's not whitelisted. Yeah, no problem. Does anyone need help? What's the problem? It's not running yet?
Yeah, it says it's looking for certificate.
Yeah, okay, so because this is running on a cloud machine, this means that you know, if they got all these requests from the same IP address here, they are probably putting you in a queue. It will not be a problem later when people run it separately. Just be patient a little bit and see if it works. Another thing, a quick announcement. So it's time now to take a group photo. That's what they told me. So we'll, in a minute or so, we will move outside here, take this group photo, and then take the coffee break. First the group photo, and then the coffee break. And while we get the coffee, I think the coffee break takes, it's a 15-minute one, but I will be here right after my coffee to help for installations or stuff like that. So if you have any trouble, just come back here after you got your coffee and we try to figure it out. Okay. Yeah, I told you that we can do it now. If you're ready with the photo, I mean, because they are waiting for their code to run and everything. It's a good time. What time is it now? Yeah.
Sorry, I'm unfamiliar with the.
Yeah.
So, yeah, I pressed run for the sensitivity matrix one.
Okay.
So I do like this. Press
Yes.
And where does it save the?
Oh, everything that is saved is out here in the output column. So if the last run is this one, then the output is this one. But this is not the output of the sensitivity matrix one, is the one of the test. Have you run? Okay, try.
Yeah, so I was here.
Yeah.
And do I press?
No, you have to press on this one. So there is an arrow on the right.
Okay.
Yeah, that one. And say set as file to run.
Okay.
And then it runs. But this is only now. I mean, later you'll have your own script, exercise1.m. You set that one to run, and then you do everything there. Okay, you don't have to change it anymore. So let me, one last bit of information. The way it works here is that here, the set, the file run, tells which script you want to run. So you have to click on any of the scripts there, say that this is the test you want to run, then press reproducible run. The output is here on the right. So all the output, there's no plots popping up or anything. If you want figures, you have to use the script save figure so that you have a PDF there with your figure. If you want anything which is output by MATLAB, you will see it here, but also in here, right? So the idea of this system, which I think you might find useful, is that if you have some code for your paper, by pressing the button, you get the figures that are in the paper, so that a person that wants to read your paper can also look back at your code and see how you generated the things that you're showing. And so you can see it here. Now, the resolution of this one doesn't allow you to see a lot, but when you run it once, you will see something here. So for example, if the test I want to run is the sensitivity matrix, I do this. I do set as file to run. And then I run it. When it runs, you will see it here. Okay? Let me show you the other one. Okay. So. Okay, so this is an example of the capsule that I had. These are typical runs. Okay, you will see the run here with the output and everything. Right, so stuff like that. Okay. Now, trust me, if the resolution was fine, it would be a bit more enjoyable.
So you can have multiple graphs.
Yes, you can save all the figures you save. They end up here. Just use the script. The function save figure. Save figure with the file name, and you will get one. But if you look at the scripts, at the test scripts here, you see what I mean. Like, you see how it's used. Save figure and file. Photo. Okay, let's go outside. Excuse me. Let's go outside for the photo, and then the coffee break, so that your code will run in the meanwhile, and then when we come back, most things will be solved by themselves. Fine now, is it working? Were you able to run something? So I suggest the following. So there was this first exercise, and this first exercise requires you to, it's simple questions. So, but to make sure we don't go too late in time, I'm sharing what was my solution to the first exercise, but without the important part, so how to compute this one. But at least you know what kind of code you would have to write. So you see here what I'm doing. I'm using load case to load the grid. This is a file that you have to write yourself and put it in the code folder and set as the one that has to be run when you click run. And you see here there is, this is the kind of script you're expected to write. You load the case file. The case file is what describes the grid, the topology, the parameters. Then I say, okay, generator buses is just number 20. And then I add the generator. I use the script add generators to add a generator at bus 20. And then R is the sensitivity matrix of this new grid. RG, if you remember, are only the columns corresponding to the generator buses. In this case, it's one column. Then I load the power demand, the historical power demand. I'm going to tell you how many data points you have and so on. The Vmax is 2% above the nominal voltage. And then I want to compute Gmax for the robust optimization. And by robust optimization, I mean the only information you have is that loads are actually positive. Then I have, you compute the Gmax in expectation, so for the expected demand. And then you compute the Gmax assuming Gaussianity. So the idea was that you have this data, you compute the median, the average, and you compute the mean and the standard deviation. And you just say, okay, then I assume it's a Gaussian, then 5% tail is 1.6 something standard deviations away. Okay? And this is the kind of code. I mean, you write your own code for Gmax in the 3 cases, and this prints the 3 different values and give you the 3 numbers, which are the one you would like to, I would like you to compute. And then if you're curious about what is the resulting voltage, so what happens if I limit my generation there, and then I see what happens based on historical data to the voltages, then you have to go to the script test, voltage distribution, which what it basically does, you say here what is your power generation that you are considering as your limit, and then this will print the power generation of the voltage distribution of the grid. So let me just run this one to show you how it looks like. This is more to see what is the result of your approach. So for example, if I here say that I do robust optimization and I think you can only generate 1.6 megawatts maximum, and then I run it. Oh, okay. Let's see. Is it still running? Did it run for you, or? Okay. Okay. But now it should be a bit fun. And then it runs. And then a bit of computation because there's some data to process. And then in this case, this is my last run. No, sorry, this one. Yeah, and with 1.6, this is the distribution. So let me see if I can open it somewhere else because this is embarrassingly small. Well, on your plot, you would see this bigger. Let me. For example, with 1.6 megawatts, this is the voltage. These are the 55 bus from number 1 to 55. This is the voltage. The way I created this script is that with all the data collected from real power demands, the bar indicates the median, the star indicates the median of the voltage, and this is the 95% of the cases. Meaning with 95% of the cases, my voltage was actually below 0.99 something, right? So it was very conservative here. I could have injected much more power because this is far below 1.02. If I do things properly, then these bars here should be close to 1.02 because these bars are the 95 percentile. 95 percentile, 5% percentile, and the median. Okay? But this is just to test. What you have to do is to write the code similar to this exercise 1, based on the information I gave you in the slides. It's literally one line per Gmax, but you have to think about what's in there. And you will get 3 numbers, okay? And, okay, I would suggest that you start working now. And you raise your hand if I need to come there because something, well, some question needs to be answered. Okay. Yeah.
Maybe just to take those 2 tables over there for the tent.
Yeah.
Sorry to.
No, of course, they are working now. It's perfect time. No problem. Hey, someone else, okay.
I already, like, I mean, I think it's set up everything, but I wanted to test, like, the things that you were running that were, like, kind of tests.
Yes.
I don't know, like, how
in the tests here,
okay.
Click on there, then you have a number of tests for at least some of these functions.
Okay.
So for example, if you do test of the, or if you do this voltage distribution one, okay, click on that one and click on the little arrow there. No, here in the, that's not the best, yeah. And then you have a set file to run.
Okay.
And now this is the one you run. Now it's a bit cumbersome, but then at the end you will have your own file, exercise 1, and that's the only one that you keep running, right?
Yes.
Just in this phase, you have to.
But all of these ones can be used or incorporated in my exercise.
Of course,
They
yes.
can be called as functions.
They will be called as functions. So especially the functions, the tests are just to show you how to use the functions, and the scripts are actually to be run separately. I mean, you might find them useful, but.
Okay. So and every time I have like the main script that I want to run, I have to set it as the running file.
Yes, but you will have this exercise 1, and that's the only one. Yeah, no problem. Sorry, can I do that?
Well, we have gotten a lot of issues. We don't really, for some reason, when we try and run, we weren't really sure how to create the post-install file.
So,
we just basically created a new file. And
no. You have to do, so remove this post-install one.
Yeah.
That's unfortunately the problem. Do on environment.
Yeah.
And then down there, scroll down, there is edit post-install file. This will create one, but with higher privileges. So now this post-install one can be run. So you copy this one in there.
So you just copy all the text from
Yes, from the other one.
Like this.
And now this should be fine.
And then where do I check it as?
Well, test the environment, for example. And you have to click on the little arrow there, yeah, and say set as file to run, and then you run it. And then it's actually creating, yeah, and it's running. Okay.
In which folder should we create the code?
In the code folder.
Code folder just here, like
Yes, just so you click
scripts.
in scripts if you want. Doesn't matter. Actually, all the subfolders are already in the MATLAB path, so you don't need to use any folder. Yeah. So, how is it if I put it on?
the fourth and the fifth point, or like one?
Yeah, yeah, it's the same thing. Yes, exactly. It's just yeah, pieces of information that you have. Yeah, no problem. Yeah.
Can I get the dimensions of a variable also somewhere here from the screen?
Which one do you need? Because it's a bit.
Like load.
This one, so you can tell from here, the number of data points is because it's called exactly the same. So let me write it here. So I think it's number 2 is rows. Rows, yeah, okay. So there is one data structure you're loading. It's called historical data points. That's a matrix which is dimension n, number of loads, which is 55, I think, and number of columns, which is the samples, and this is many, thousands, hundreds, I don't remember, okay? You have a number of data points, size of historical power demands, comma 2, which is giving you exactly this one. So this is number of data points, okay? And it's just a matrix. There's no, it's not a structure. There's just a matrix of power demands. The important thing is that you get the workflow up and running. We'll, in 5 minutes, we will continue with the slides. If you don't manage to do this in these next 5 minutes, it's okay, in the sense that we move on. It's something you can conclude later when we do the second exercise. You resume from here. But it's also important that we see the rest of the slides. So just make sure everything is working. I mean, you can write your code and you can run it. Otherwise, raise your hand.
So I just have a question about
Yeah.
the robust optimization. It means to have a worst case.
Correct.
So, yeah, so it's like for one column of the data set, we have a solution of the GI, or we pull out.
No, because this is something that you have to solve this one for all possible demands. So for all possible.
Also, so include all the data at the same time.
Yes, but in this case, it's actually robust with respect to the only information, even before you know the data, you only know that loads are positive in a way.
Okay.
Okay.
So
you know.
cannot from the data determine which one is the
I mean, that's another option that I haven't
okay,
presented. You could also say, okay, what is the minimum load I've always observed, and I use that one. It's the same, yeah.
So what you expect, it's
I would expect here with just the demand being
Okay,
0,
okay,
because
okay.
that's it. Yeah.
How will we get those plots visible?
Oh, they are just saved here in the output. So if you use the save figure, then that creates a PDF, which is somewhere here. Yeah, go up, and then there should be, if the run was successful, then there should be a file. Yeah, but when it's only output, it's only text. It means it didn't really save anything.
Okay.
So you need to make sure it runs. Yeah. Make sure it's running this one. Yeah, exactly. Yes, this is the one where you test the accuracy of the, yes, correct, exactly. Let me go here first and then I come there.
I don't really understand which optimization. We're writing the optimization problem now, right? So I don't really
Yes.
understand which. Like, are we using YAML or MapPower or what?
You're going to do it by hand, in the sense that this is only one decision variable. Okay. It's only to find Gmax.
Okay.
And so.
I'm not actually writing an.
No, you're not writing an optimization problem, because it's the max is the worst or the mean is just one-dimensional, and so your solver is going to be find the mean of something.
Okay, so I'm just doing it by hand.
Yeah, for the robust one? Yeah. Yes. So, okay, let me make a comment to everybody on this one. So for the robust optimization one, there was a bit of, not confusion, but there are 2 ways of doing that. I said that in that case, you consider the worst possible case. And you could interpret this one either by saying, okay, I don't know anything about the loads. And so for me, the worst possible case is that the load is 0. The demand is 0, so the voltage is the highest one, because I know nothing about these loads, right? And another option is that I take the data and I take what was the smallest demand, in some sense, because it's not an easy answer. What is the worst case in the data? They're both valid, right? There are two alternatives. If you have the data, you can use it, but one option is also to say, I know nothing, I only know that power demands are always positive, they are a demand, they are not an injection, okay? You can try both. It's the same procedure in a way, but one is a bit more conservative than the other one. Okay. Oh yeah, sorry, it's, yeah. Not sure where. This way. No, it's okay.
So we're confused with what is like input power generation. So in the PF solution, you like create a power generation. So how do you decide this stuff?
Which script is this one?
Is test PF solution? Or should we use this function?
Yeah, but this one is when you have two generators in this case. So it's a bit confusing. Otherwise, this power generation is just a scalar number, which is the generator of the power injection of the only generator. So in your case, it will be a scalar number. And it's the power injected by that generator.
How do you, if this is an input parameter, how do you choose it?
Oh, it's the one that you compute, like the Gmax, the result of your robust optimization. This is how much is the... So you don't use this function to compute this Gmax.
So how do you
Just by
No, so this Gmax is the one you compute. So this Gmax is the solution of, I don't know, robust. Is the solution of this one, right?
How do we turn that into code?
What is the framework for
Because
objective function?
no. So the objective function is that you're maximizing a number, right? Because it's a scalar number. And then the constraint is that the voltage.
But how do we do this in MATLAB? I don't know how to set the objective.
Well, it's the maximum of a vector. So just a comment. So these are optimization problems. The reason why I had only one generator, it's because this way, you don't need any solver to this one. You are maximizing a scalar number subject to V of GD being less than Vmax. V of GD is 1 plus R G generator minus R demand. Okay, so this is an inequality, and you have one scalar element that needs to satisfy this equality, well, for all possible, for D in D, or for D in expected value of D, or D from the Gaussian, whatever, right? But these are inequalities, and you have to find the largest G that satisfies this one, which doesn't require a linear program solver or anything. Is the, just do it for all possible D and take the maximum one. Or you want to maximize and satisfy this one, is the minimum one. Is it clear? You want this one to be true for the worst case. How does this look like? This is RG less or equal than Vmax minus 1 minus plus RD worst case. Okay? I mean, this is a vector, this is a number, and this is a vector. And then from here, I don't tell you how to do it. Okay. Oh, the whiteboard, sorry. Better? Okay, bear with me for a second. I'll move back to the slides. I want to continue with a little bit of information on the slides. This one, you should have an idea now of how to do it. You will see the next exercise builds up on this one, so then you will have time for this and the next exercise. The second part is much shorter, so you will see. So this one might be the only part which is a little bit trickier because you need to make sure you have to compute this quartile or this 95 percentile for the power distribution. So it's the only one which is a little bit trickier than this one, you will see. But it should be doable. Let me show you an extra way of solving the same problem. So I mentioned this chance constraint, right? And I said a tempting idea is to assume everything is Gaussian so that this probability can be computed explicitly, okay? I'm going to spoil it for you. It doesn't really work very well. And you will see why. I mean, it would be interesting to understand if you also try to guess why it's not working well in this case. Is this Gaussianity assumption satisfied or not? Why is Gaussian such a bad thing to use? And what I'm going to show you now is an alternative solution. It's an alternative solution. So the scenario approach that you've already seen a little bit is the core of it is this following operation. Instead of this chance constraint, so the probability of the voltage violation being smaller than 5%, or the probability of satisfying the constraint larger than 95%, you replace it with a large number of deterministic constraints, right? Constraints of this form. The voltage needs to be smaller than Vmax for capital N possible demands, okay? The key point where you can do this substitution is that, first of all, you need to know exactly what is this N. So how many do I need here? If N is infinity, then you're back to robust optimization, right? You're saying it needs to be fine for every possible D. But it's actually for a finite number of N. And the other key point is that these disturbances here, these samples, they need to come from the correct distribution. And I told you that assuming it's Gaussian or stuff like that doesn't really work well, you will see. How do you sample from the correct distribution, the same distribution that you use in the probability here? And the idea is, of course, to use data, because by definition, the historical measurements of power demands are samples from the same distribution you're trying to use in an optimization. So instead of saying, oh, I think the distribution is Gaussian, I think it's Poisson, I think it's uniform, I just say I don't know the distribution, I don't even try to identify it, but I just take samples from the same distribution, which I'm sure is the correct one, okay? And so the scenario approach, you will have to replace this probability constraint with just a large number N of constraints that you take from your sample. So you have hundreds of this one in the data, you just take, you don't need so many, right? You need a little bit less than that. How many do you need? For this one, I'm not going to cover the theorem, I'm just going to tell you that there is a theorem that gives you exactly how many samples do you need to extract to be sure that you are satisfying this 95% probability criteria. And this theorem says the following: suppose that I give you an epsilon, which is this violation probability, like the 5%, and I give you beta, which is a confidence level, and we'll see in a second what it is. Then if N satisfies this equation, that, by the way, you don't have to solve because there's a script for that in the code. If N satisfies this equation, then the solution to the optimization problem up there, right, to this one, satisfy the original constraint that I wanted with probability larger than 1 minus beta. So there are two probabilities, be careful here. One is the probability of violating the constraints, is the one that comes from your specifications. Now you take these n samples, you use them as hard constraints, and with probability 1 minus beta, this is actually the same as the probability. I mean, the two results are actually correct. Okay? So this is more like how much you trust your method. This is your specifications. Because, of course, you could be very unlucky and say, oh, I want to take n samples that I compute based on epsilon, but then you are so unlucky that these n samples are all the same sample for some reason, right? Because you have some randomization in how you pick these samples. This is in beta, okay? Then in the exercise, I tell you exactly what to use as beta and so on, but that's the idea. There is a value of n. If you give me the violation probability that you want at the confidence level, I give you n. There is a function that computes n for you, okay? And I want just to make a comment on how big is this n. So n depends on many things, but there are 3 parameters which affect n the most, and I like to discuss. One is that n depends, and that's a bit weird, on the number of decision variables. So how many n do you need to pick here depends on the number of decision variables, so on the size of G, okay? Which is a bit weird because the stochastic part here is D, right? But because you're using it in a convex optimization problem of the dimension of G, then the many n you need depend on the dimension of G. This is not obvious. This comes from the theorem, right? But it's very good because G is a scalar number, while the number of disturbances is all your smart meters in your system. So it would be very unfortunate if the number of samples depends on how big is your system. It's very nice that the number of samples depends on the number of decision variables that you have, because that's much smaller, right? You have 2 generators, you have 5 generators, and you have 100 loads, okay? And here is an example, like if you fix the rest, with 1 decision variable, you would have to pick 100 samples, with 10 decision variables, 400, with 100 decision variables, 2,000 samples, order of magnitude, okay? Then n is also, of course, a function of the violation probability. So if I want my voltage constraints to be satisfied 90% of the time, then I only need 100 samples. If I want it to be 99% of the time, then it's 1,000 samples. If I want 99.9% of the time, then I need 11,000 samples. That's the tricky part. The n scales very badly with the violation probability. And the third one is this beta, which is this confidence level. So how much you are confident that the result actually corresponds to what to the solution of the chance constraint optimization problem. This enters logarithmically in n. So this is never a problem. If you want to be sure with 1% probability that the method is not working, you need 165, 1,000, 200, 10 to the minus 4, 270, 10 to the minus 5, 300, right? Beta enters logarithmically in m. So even if you want this one to be 10 to the minus 10, you would have to add a few samples. It's fine. Beta is never a problem, okay? But notice what this is doing. This is turning a chance constraint optimization problem into basically a robust optimization problem, just with a limited number of samples instead of all possible samples, okay? And because you have, this is exactly the equation I wrote here, because after you apply these scenarios, after you pick the scenarios, you have all these constraints with 1 goes to 1 to n. Remember, we are in a linear case, so we have equations of this kind here, okay? But you have one of these for every sample, okay? So for every sample that you take in terms of demand, you have one of these one. While for the robust one, you have the worst case D here. And now you have one of these for every sample. There are many, okay? But they are all linear inequalities, okay? So this is a bit easier because it's linear inequalities and you're trying to maximize a linear cost function. This is fine. And what I wanted to, the reason why this will use it more for the third exercise, but what I wanted to mention is that large sets of linear inequalities actually have a very nice mathematical but also computational representation, which is polyhedra. So a polyhedron is exactly a set, is the set of points that satisfy a large number of linear inequalities. Each one of these linear inequalities is one of the face of this polyhedra, right? So this one or the equation up here are exactly the same thing, but this is a very, this is a good object to keep in mind, and that's why I've included it in the script, because there are some numerical routines to work with polyhedra. You can intersect them, you can cut them, you can sum them, you can do stuff. You can plot them, okay? So for the second exercise, you not necessarily have to do this thing with the polyhedra, but keep in mind that there is this interpretation, right? You could take, this is just a large set of linear inequality, one per sample. So instead of the worst case here, you have sample 1, sample 2, sample 3, sample n. How many constraints do you have is n times the size of this one, right? So it's really a lot. It's going to be hundreds times 50, okay? So thousands. But it's okay. The optimization problem that you're solving is a one-dimensional linear program. You have to find the largest G that satisfies all these linear inequalities. It's a scalar search problem. Just take the one which is constraining you most. Okay, so polyhedra, that's exactly what I said in words, are nice mathematical objects. They are low dimension because the dimension of the polyhedra, remember, is G. In this case, this is a scalar polyhedra in your example. And very large number of constraints are not a problem. So I told you, these are 5, you will have like thousands of constraints in this problem, but in one scalar dimension. What this means is that I have an ax, like I have xg, my only decision variable, and I have 5,000 constraints, right? All saying that you need to stay on the left of the constraint. Now, as you can see, how many you can add as many as you want, but the representation of the feasible region is very simple. It's just the smallest one of all, okay? And this is very typical in this application. When you do this kind of problem in low dimension, like you have 2 generators, 3 generators, something like that, and you have 5,000 constraints, not all constraints are actually meaningful. Most of them are completely redundant. So this is not for the experiment you have seen, but it's for another one. This is 2 generators in this case. Don't look at the voltage there. It's 2 generators. And we generated, I think, 300 samples times the 13. This is also thousands of different sets, polyhedra. And then actually they're all redundant except for one, the one in the middle, right? So the representation of this polyhedra, even if it has 5,000 constraints, is actually 7 constraints. 1, 2, 3, 4, 5, 6, 7. Okay? And this is something that you would observe typically in scenario approach, where you have a huge number of constraints, but for a problem which is low dimensional, and this, unless the problem is very pathological, means that a lot of these constraints are not active. You can just drop them. So the only pathological case is that you have one constraint like this one in 2 dimensions, and the other one like this, and then another one like this, and then another one like this, and you're making a circle or something, right? Then they're all active. But in most cases, this is not happening. Most of the constraints can be eliminated. And there are numerical routines to eliminate them. You don't have to look into them. You have these 5,000 constraints. There is a script that says eliminate redundant constraints. It takes a bit of time, like a minute to run, so make sure you run it when everything else is cool. But then you're left with 5 constraints. This means that this entire chance constraint optimization problem at the end becomes an optimization problem with 5 constraints, even if you have thousands of data points from your smart meters. Okay? And so this is the second exercise. It's exactly the same setup. That's why I wanted to mention it now. Exactly the same setup. The historical data is exactly the same. By the way, this is Danish city of Horsen, which I'm not sure where it is. But this is historical data collected from here somewhere. And then together with the other one, now you have to compute the optimal curtailment with this scenario approach. I'll tell you which beta to use. And you can use, you can do it by hand because I told you it's just a mean operation, or you can use the MPT toolbox. The MPT toolbox allows you to work with polyhedra. You can see this test file to see what happens. Okay? So this experiment is actually just one extra line of the previous experiment. It's just compute Gmax for the scenario approach. Okay? And then you can see what is the average generated power now. Is it really satisfactory or not? Okay, I wanted to add this one because now some of you might already start working on the scenario. Questions, yeah?
So you talked about how the whole polyhedra reduces the scenario.
Yes.
Can you comment on how important is the selection of the method of generating scenarios?
For eliminating one or for sampling them?
Because we might end up with, let's say, 8 rogue scenarios which are somehow wrong.
Yeah, yeah. So in the sampling of the scenario, in the sampling of this, yeah, so that's exactly what goes in this beta. So you might be unlucky, and you might have, so if you run, let's say you write your code for chance constraint optimization with the scenario approach, if you run it twice, it gives you 2 different numbers, because every time you have different samples. That's why you have a probability that you're actually screwing up there. You're taking the wrong, but this is small. I mean, if you run it, it's going to be fine. And remember, these are all inner approximations, and so they're all conservative a little bit. And you know, it might, depending on your sample, they might be a bit less or more conservative, but not too bad. If you take hundreds of them, it's going to average out. Yeah. Any other question? Okay, then let's work for keep working on the first exercise and add also this second one. Because then in 10 minutes, maybe, I would like to introduce the last part. You should be able to write some of these tests in these 10 minutes. If it's not, then we can continue later at the end. I don't want to break the flow too often. Okay? Good. Yeah. Hi.
I'm not very familiar with this,
Yep.
so maybe I missed a step, but I filled all of this in. Which is it? Not showing this one.
Mm-hmm.
And oh, there.
Yeah.
No,
Yeah, this is.
it's not showing. But when I
That's
try
fine.
to run it, then I'm not sure what I should be adding instead of the question marks. Am I supposed to run one of these files to get
No,
the
it's
maximum generation?
no, it's one line of code yourself. That's where you compute this Gmax, and it's going to be the solution of the optimization problem I wrote there on the board.
So if I can quickly.
Yeah.
When I double clean it, it just doesn't open it? Oh.
Yeah, so this
There
is.
you go. So because you mentioned 1.6, I just put 1.6
Yeah, sure, of course, yeah.
there. But when I try to run it, I still get the...
Yeah, but after the 1.6, you need to do, okay, the voltage is fine, yeah.
Okay.
Voltages creates this, the voltage distribution, but then this is not saving, so what is done here, you're setting Gmax to 1.6, and then you're computing the voltages, and then you're not using them, right? So
Okay.
if you want to use them, you need to, so if you go to voltage distribution,
Okay.
there's all these, after there's all these things to do.
Okay, so
But
I'm
then the
supposed to
easiest way is that you take that 1.6 and you plug it in here and you run this one.
Oh, so like
Yeah, like
just
that.
run this then.
Yes.
Okay, okay.
But just do it as a kind of to verify what happens when you try and see
Okay.
when you have computed your Gmax. So the exercise file only writes out, I mean, prints the Gmax,
Gmax
and then
for
you can
different
copy
things.
them. Yeah, exactly.
Okay, okay, I see. All right, thank you.
No problem.
I'll
So
give it a
let's
go.
check if it's.
Still trying to...
Yeah, and then error bar is the. Yeah, this is what will be the voltage of the feeder for 1.6 megawatts of injected power.
Okay, I see. Okay, thank
Okay.
you.
Charger.
Okay, thank you.
Still needed.
Yeah, yeah. No, now they borrowed me one from here somewhere.
Okay.
I think it's going to be charged for the rest of the day. It is 8 hours. How's everything? Yes.
Good. So we just finished implementing the distributed controller on at least Alex notebook. So there everything's running
Okay.
fine.
Okay.
And now we just need to push. So the next step is actuating the devices from his notebook. So
Okay.
then we basically have the same setup on his Python
Yes,
code
it's only
notebook.
running.
Then I have
yeah.
on my MacBook with MATLAB. But then it should be really easy and just press of a button to distribute this code to the controllers, and then everything should be fine.
Okay.
So let's see.
And it works. It works like it regulates the voltages and everything, right?
We do not actuate yet.
Okay. Okay.
So that's the next step, but that shouldn't be a problem. I mean, that's just adding.
If it works there, yeah.
So yeah, that looks good.
Okay.
And everything else we can discuss later.
Yeah. Okay. Yeah, I'll be done. It should start at 1:15. I think it will take a bit longer, but let's see. Let's see what happens.
Yeah, then
because they're a bit
I will
late.
grab lunch with Alex now. And,
Okay.
Then I'll be back at 1:15 over.
Okay, so I left this one. Do you need it now? I'll keep it and then
I'll. Battery, but I can do that for a day. So
okay.
just
Okay. I'll give you back. Yeah. Thanks.
So do you want to talk during lunch, after lunch?
I think even so. When I have lunch, you are probably already done with lunch, right?
Yes.
Yeah. So we can talk over my lunch. It's fine. During my lunch is okay.
Okay.
Maybe I can text you on Slack when we're done here, unless you want to stay around. But
yeah, or I just join you for.
Or
lunch
just
here.
join. Yeah, I think we're going to go for lunch at 1:30. No. I mean, it's going to be. Yeah. Exactly. Perfect. Okay. Yes.
Sorry, I missed maybe something crucial because when we are doing those exercises 1 to 3, so do we have some template which we complete or write our
No. So it's I showed one on the screen. I can show you again. Yes, 1 second. I'll be back in a second. So this is an example, but it's not that you have to use this one. It's just that's my solution to the exercise. Yeah, you can use this as an inspiration, but yeah. So, someone was asking, yeah, you're asking.
Can you tell us, like, in the code, like, how do we get this, like, G and D? I mean, that they're like the power demands, and
yeah,
like, where are they in the in the data structure?
Which one? The historical data? That's only D.
It's called D.
Well, no, it's called historical power demands. That's a vector of dimension. I removed it. It's a vector that goes from.
So this is kind of.
Yeah, that's D. But
And
that's
the
just
G,
all
where
the historical.
I picked the G I have to pull out of the test.
G is the one. Well, no, G is the one you compute in a way, right? G is the
Optimize over.
you optimize over G. And D, remember, the historical power demand is like 1,000 of columns. So the D that you have to pass to, I don't know, to the grid, to the power flow solver is only one column of that.
So which one?
Yeah, I mean, it depends. These are all samples, historical samples, right?
Okay, so it doesn't matter. So I have to first check the size of this.
Yeah, this should be like 55 by
something.
Yes, exactly. Question?
What is the generation then in the first, in a robust way, where we assume like the worst zero demand?
I would have to run it. Do you know the answer? Okay. So just to see if you are on the right track, the robust optimization one. So robust if you only assume that the power demand is positive numbers. So you don't use the data at all. You just do the worst case for 0 demand. That's around 1.4 megawatts of maximum active power injected. Okay, about. So if you write the correct number, it means you have done it. So the G max and by robust, I assume that the uncertainty set is all positive numbers. Okay. So at least you have an idea if you're doing things correct or not. Yeah, first exercise, the robust one. Does it make sense?
So, for me, it doesn't make sense. We just compute it in one line, but where's the optimization? I mean, it's like robust, but...
So wait, this is exactly, I mean, this is...
so,
RG.
The robustness is in formulation, right?
Yeah, just be careful. I think, I mean, that's correct. In the robustness, it's in the formulation. You say that when the demand is 0, then your V needs to be less than V max. And so you basically wrote that one, RG less or equal than V max minus 1. Yes. The only problem is the RG inverse. There's no RG inverse. RGR or the R up G. This is actually a vector. Or is this the inverse element by element?
Yeah,
Sorry.
but we are
finding... no, it's element by element, yeah.
And then...
so yeah, but then this is now a vector.
Yeah, I have a vector.
Yeah.
But how I get this value? Like, how did it compute?
No, but that's so of that vector, so this is the vector.
Yes.
So as dimension 55.
Okay.
Because this is basically the limit at every bus, for the voltage for 1 per bus.
Okay.
You want the voltage to be satisfied for every bus, and so it's the smallest of that one. So go back to the output. The smallest of this element, which is, I can tell you where it is, go up a bit, 1.4. Yeah, that one.
Oh.
Okay. Because this is, so these are 55 constraints. And they all need to be satisfied. For them to be all satisfied, you have to take the smallest of the G max, the one that satisfies them all. Okay?
So I can just write min function?
Yeah.
On the first one, so we don't need to actually check the condition because we have just one
yes.
generation, so we can just find the maximum.
Yes.
So we use this condition actually to find the generations, right, from the Z1 plus R multiplied.
Correct. Yes.
Yeah. So, but when we do so, this is V max minus 1s, but we have to multiply also from the left-hand side by RG in inverse matrix, right?
Yes. Well, RG is only a vector, so you have to do inverse element-wise. So you basically have this equation, right? So this inequality, okay, and this one are 55 constraints. And now you have to find what is a value of G that when you plug it in here, all these are satisfied. Element, yeah. So these are 55 separate constraints in a way,
so
right?
It's going to be this one, right?
Yeah, but that's the max. If you want a value that satisfies all of them, it needs to be the mean.
Sorry, I need to find a minimum.
Yeah, and then it's correct. No, it's
just one thing. Yeah. When do you plan to finish?
So we
were
started.
planning to start that lunch at 1:15, but if you need a few extra minutes.
Yeah, I will need a few extra minutes.
Maybe 1:30.
Yeah, 1:30 will be fine. For 1:30, we'll just call
tell
it.
them
Okay.
1:30 to go
to the tent.
Yes.
Okay, perfect.
That's 1:30.
Yeah.
That's sharp on.
They're going to be hungry.
Yeah, but also because I cannot keep the grill.
Okay, open no longer.
Yeah,
Do you want to be early, like 1:20?
No.
1:30 sharp.
Sharp.
All right. Okay. Yeah.
Can I just ask you, so I understand like something. So
yeah.
what we're supposed to do is that we have this equation.
This is the robust one?
Yeah, the robust one.
Mm-hmm.
So this is the equation. Here's the robust one.
Yep.
Okay. So we have this one, and then we wait. Didn't you formulate this one here? So you have this. This is the one.
Correct.
Yeah.
Yes.
Put the minus sign here.
Yeah. Correct.
So then, if I have like the worst case scenario, so
okay.
either the minimum of the historical power demand.
Yes.
Or zero.
It's a bit tricky. The worst case, if you take historical data, is not the minimum of the demand. Like this, you would have to do the minimum of R times D. Because that's the worst case that you have observed for this optimization problem.
Right.
It's not that so imagine, for example, that R is 0 somewhere. Yeah. Some demand is not even accounted for.
Right.
If that is 2000, doesn't matter.
Yeah. Okay.
So you need to do the minimum, the worst case of RD. Yeah.
But because R is the matrix that translates from demand to voltages in the different. Yeah.
Exactly.
Okay. So I need to make sure that my voltages are like under a certain limit.
Exactly.
On the nodes.
Yes.
So otherwise, now I'm basically cross-checking the lowest demand with the highest sensitivity to high voltages.
Yes, exactly.
And that will never happen.
That will never happen.
Yeah.
It might not be connected there,
no,
right?
Exactly.
I mean, it's not there in general.
Okay.
If you do the RD and on that one you consider the worst case, then it actually helps.
Okay.
And it's the minimum across samples, not the minimum across buses. I mean, these are okay. So that you do two mean.
Yes. Okay, so I think
it's actually the mean.
Across samples. So samples
yes.
Was the first one?
Samples was the second one. Columns.
Okay. Second one, and the bus is 20. Or
no. Actually, you have to consider. Remember, this is RD, and you have to consider RD computed for every possible power demand.
Yeah.
So you can do R times the historical power demand. It works.
Yeah.
That's why I made it this shape.
Okay. Yeah.
And then you get a longer vector now of 55 voltages for every column.
Yes.
And you have thousands of them, and then you take the small
over the over the scenarios. Okay.
Yes, exactly.
The minimal value of the scenarios. Okay, I get it.
I mean, these are also. It's not wrong to say, oh, what is the minimum or the worst case, and then assume that the same load is everywhere, but it's going to be too conservative.
Yeah.
Yeah.
And in the second case, then
yes.
you want to look at the scenarios. So then what we need to use this PF solution function, right?
Not really. You just need to assume it's linear. So you just use the capital N samples of the disturbance, and you assume that is the, that the problem needs to be satisfied for all those scenarios.
Okay.
And then it's basically that equation, Rg less or equal than Vmax minus 1 plus Rd, but you have capital N of these equations.
Yes.
So you have to stack all of them together, and then and then solve for G.
Okay. Thanks.
No problem. Someone called me.
Now we want to solve our problem, so we want to maximize G with constraint. How we can define this objective function constraint?
Oh, there's no objective function. It's just the largest, right? So if each of these constraints is telling you what is the maximum G, and you want to find the largest G that satisfies all these constraints, so it's just the minimum of all the G. one per constraint, right? So for every constraint, you have a G max, and the minimum of them is going to be the solution of the linear program. So you don't need to use a solver or anything. It's just you just have to list all the constraints, and then you're going to have a vector of G max, and you take the smallest one. That's how you do it. For which one? For the robust? Yeah, it's a bit tricky. It's not the minimum of the demand, but it's the minimum of RD. Because what you're trying to do is what is the worst possible D sample for my optimization problem, right? It's not necessarily the minimum demand, because the minimum demand it depends on the sensitivity matrix as well. And D. Exactly. So for example, if you have one sample when there was a large demand in a node close to the substation, that's not worst case. Maybe the worst case is a relatively small load, but very far away. So you need to compute the minimum of RD.
Now, in this case study, we should calculate R or we have it in the...
No, R is already here. R. You have it from that line. Yeah, I did it right. Okay, I've seen that some of you is already on the right track, so I answer the last question, and then I resume with the final part of the lecture.
This is very vague.
Yeah.
I have no idea what we're expected to do
Okay.
in practice. So this is just for exercise 1.
Yes.
I'm not quite sure what's expected of this. So are we meant to optimize something like using the formulations?
You're basically expected to find the solution to this one, yes, which is going to be a scalar number because G is just one-dimensional.
Okay. So we're meant to set up an optimization problem inside this code then?
Yes, but it's you could use like limprog or others, but this is a scalar problem, so it's basically maximize G, number G, subject to many constraints. So the only thing you have to do is to find the largest G that satisfies all these constraints, or you just write all these constraints and you take the smallest one of them. Like imagine that you have to maximize G subject to 3G less than 5, 4G less than 12, and so on. You take the smallest one. That's the solution of the linear program.
Okay, and how do you do that in practice?
I mean, there's no optimization to run. It's just you compute these constraints 1 plus RG minus RD less or equal than V max.
So
these ones. The only tricky part, or this one is the same. The only tricky part is to find D, and this is just a list of constraints. So let me conclude with this comment because I see the same question a couple of times. It's not a linear program that you're trying to solve, in the sense there's no solver to call. No matter which one you use, like robust optimization, chance constraint, the expected value, whatever, at the end of the day, it turns out it's only a matter of how to choose the disturbance or the demand for which you want the voltage to be fine. Is it the worst possible demand? Is it the average? Is it the samples, or so on? This means that the only thing you're trying to do is to solve, to find the largest G that satisfies these equations. I say these equations or inequalities because this is a vector, right? These are 55. There is one per voltage. So the only thing is you need to find the G, the max G, such that these are satisfied. And to do that, you basically just have to write this one in a decent form, G less or equal than a long vector, a huge vector, because it is, in the worst case, this is 55. In the scenario, this is 55 times number of samples, and so on. And now to find the largest G that satisfies all these inequalities, you don't need a solver. You need to pick the largest G that satisfies this one. It's a scalar problem, right? You have to find a G that satisfies G less than so many numbers. These are now numbers. If you plug in the disturbance you want, or the demand you want, could be the worst case, could be the samples, could be the expectations, whatever, you're left with a mean problem, right? Okay, that's why those lines where I have the question marks, they're actually a one line. That's a one line MATLAB.
So when we sample,
second exercise.
Yeah.
Resample. So in all constraints, we replace D with the average.
When you sample, no, you can stay with the sample. We made the sample. The sample as it is. Yes, yes, correct. Okay, so let's move on with the last part. It will take up to 1:30. So at 1:30, lunch is ready. So you'll have to stay with me for another 30 minutes. I'll present the last part, which actually is something original and new. It's not the classical chance constraint with scenario. It's slightly different, but it's basically a variation of this one. So stay with me for these next 20 minutes, and then I'll present the last exercise, and then we are done. Okay? Okay, so third part is, first of all, in terms of method, in terms of theory, what is the take-home message of this one? If you run these numbers and if you write the G max for the different cases and you see what is the corresponding voltage distribution, then you will see that the specification for the power grid are very well represented by the chance constraint. So you will see if you do the robust one, you're very conservative. If you do the average, you are too optimistic. If you do the Gaussian, I'm not going to tell you what happens because that's trickier. If you do the chance constraint, then you really have this nice 95% probability of violation, right? It works very well. And it's what practitioners would like to hear. Your curtailment is safe for 95% of the time. In this last 5% of the time, I might have to do something at the last minute. And the second take-home message is that the probability distribution of the uncertainty is incredibly important. In particular, and here is a bit of you will see when you do the Gaussian distribution, what's important is the support often of these disturbances, right? So if you know that your demand goes from this value to this value and anything in between, there's already a lot of information. If you forget this information, you say, no, I think it's Gaussian, let me just take the average and then the variance, what you're doing is that instead of, in the scalar case, you have these points, you measure the demand only on one load, right? It distributes like this one. For chance constraint, the important thing is that you never observe something less than this one and nothing larger than this one. And actually, often you are between here and here. That's what chance constraint learns from the data, that this is the typical demand. If you say, but I think this is Gaussian, and they say the average is here, and the variance is, I don't know, this one, then my Gaussian is this. This is very bad, because Gaussians have infinite support, right? Gaussians have very bad tails here. Your 5% is going to be somewhere far away. It's like saying, oh, because my car can consume 1 kilowatts when it's on and 0 when it's off, then with some more probability, it's actually injecting -5. No, right? There is a finite support, right? And that's what you will see in the last point of the first exercise. Then data are what we use for the scenario approach. And with these polytopes at the end, you should realize that scenario approach becomes very tractable once there are a few decision variables, because you have a polytope with thousands of constraints, like these ones, but you're choosing one number. That's why it's simple. You don't need a linear program, right? You just need to do a mean operation. If it's in 2 dimensions, it's not that simple, but it's still, you have a polytope, a polyhedron in 2 dimensions, so in 2D, with thousands of constraints, fine. Most of them are useless. Okay. And now there is the last part, which is a more interesting problem, according to me, and is the following. Suppose that you have all this data from the past, from the smart meters, but you also have one measurement, or a few measurements, right? These measurements are in real time. For example, this is the example you will see in the third exercise. You measure the total power demand of the grid because you have a sensor here. It's the only sensor you have in real time that tells you what is the total power demand of the grid in real time. And you can choose your curtailment based on that one. There's still a lot of uncertainty, right? You don't know anything about the demand. You only know that the total demand is 1 megawatts, right? How do you use that? Well, the problem, you cannot use the scenario approach as it is. The problem is that these historical data are not really relevant. Like, suppose you measure 3 megawatts, you have these thousands of data from the past, and you look at what was the total demand in all these samples, if the total demand for one sample was 1 megawatt, is it really useful for now? I mean, this is a different setup. This was a day in the past where the total demand was 1 megawatt. Now it's 3. Is that information useful to be used here, right? To be used in the chance constraint one? It's not clear, because this was clearly not the case I'm looking at right now. And it's very tricky to work with data points so that you actually get useful data points. Because in a continuous world, if you look back, there's probably going to be no sample where the demand was exactly your demand now, right? Now it's 1.255. You go back to your thousands of points, it was never exactly 1.255. Even if you say, okay, but I will accept a bit of tolerance, well, you remember, you need a lot of measurements with that demand. So especially when you have multiple measurements, like together with the aggregate demand, you also measure 1 voltage somewhere. It's very hard to go back, look at samples where these measurements were the same, and say, okay, and then I want 2,000 of these points, right? You typically don't have them. And the worst case thing is that even if you had this data, because you've been collecting data for 10 years on this distribution grid, what do? Do you have this large database of millions of points that you keep available in a database so that when you have a measurement from the substation, you search through all of them, you find 5,000 of them, you compute the intersection, you do the polytope, you truncate it, and you choose. That's quite unrealistic, right? I mean, that's not going to be embedded in the system, okay? And so we're going to see a solution to that one. And it's the following. So first of all, we restrict to linear measurements. I told you already why we need linear stuff. So our measurement is y is h times d. Okay, we have this linear measurement on the uncertain parameter of the system. For example, h is the vector of all ones because we measure the sum of d. Okay, that's just an example. Okay. Now, how does the chance constraint optimization problem looks like when you have this measurement? Same as before, maximize the total generation subject to the probability of violating the constraints being, or satisfying the constraints, being larger than 95%. The only difference is that this probability is now the conditional probability. This is the probability with respect to d, which is the unknown, but constraint or condition to h times d being the measurement you observe. Okay? Everybody knows about conditional probability enough to parse this equation? Okay. When you say P of A condition B, it means I don't want to know the probability of the event A in general, but assuming that B has happened, right? I want to know if you have a cold, given that you're coughing. Because if I only want to know if you have cold, then it's probably 0 because nobody has it in general. But given that you're coughing, then it's very probable. And this is what's happening, right? This is condition that I observe a measurement. The probability needs to be large enough. Okay, that's the only difference. That's how the chance constraint problem looks like. And now the problem is that I showed you before in the take-home message that the samples you want to use for the scenario approach, they need to come from the exact same distribution you are using. If you do another distribution, like the Gaussian one, it's very bad. So how do you sample from this conditional distribution? And this is the only tricky or technical part you'll have to parse and to understand here. I suggest this approximate way of computing the conditional samples from the conditional distribution. I define 3 objects. One is the expectation of the demands. Easy, right? You take the average from the past. Another one is the covariance. Easy, you just use the cov command in MATLAB, it gives you the matrix, right? And then you have a K function, K matrix, which is a combination of the covariance and the measurement matrix H, okay, as it is. Now consider a random variable, which I have this weird notation for. This is the d hat condition to y. It's just a transformation of the original random variable. The original random variable was d. And now I'm doing d plus k y minus hd. So this, you can see, depends on y, depends on k, and it has transformation on d. Okay? Think of this as a transformation of the samples of d, right? If I give you a sample d for the power distribution, for the power demand, I can compute this transformation here. It's an affine transformation once I also have the measurement. And this, importantly, is this what I'm claiming, and this approximates the true conditional distribution of d given the measurement y. Okay? Is it the exact conditional distribution? Well, it's easy to show it's not. This is in 2 dimensions a uniform distribution. Here I'm saying the distribution, original distribution, is random points in the square there, right? Then I apply this transformation to each one of these samples, and I get the dark dots here, okay, on this line. Is this are these samples from the true conditional distribution of d subject to the measurement? The measurement is this black line here. So the measurement I'm using here is a measurement that tells me, yes, it's in the square, but I know it belongs to this line. Instead of computing the distribution, I take samples from the original one and apply that transformation. I get the black ones. It's good enough. It's not exact, right? Because you have points which are outside of the square at all, and they cannot exist. Okay. Now here is the Gaussian distribution. These are level sets of the distributions. The white dots are samples of the unconditioned distribution. This is the measurement, so I know the true measurement actually belongs to this line, and these dark points are the result of that projection there, of that operation. You can see it's a projection on the line. Is this exact conditional distribution of the Gaussian? It's hard to tell, right? Well, it is. So the nice thing about this operation that I proposed is that this is a linear operation, or affine if you consider y as well. It's consistent with the measurements. So if I do the measurements on my projected samples, I get exactly y. It's a simple operation. And for the Gaussian case, that's exactly the conditional distribution. Okay? So the transformation I proposed is a transformation of the samples, that you take these samples, you take your measurement, you project these samples using this simple transformation, and you get samples which are now consistent with the measurement, and they're distributed approximately as the conditional distribution. If the original distribution was Gaussian, then it's actually the exact operation. Okay? And actually, there's not much more you can do. Like, if you want a linear transformation that is exact for the Gaussian case, you don't have any other degrees of freedom. You get exactly the expression I listed, right? So if you want to stick to linear operations, which we want, that's the best you can do, is to do this projection. This is the idea, d plus k times the distance from the measurement. And this is your approximation of the conditional distribution if you don't have more information. Okay? This is the proof of the third point. I leave it for you for a bedtime read. Is it good approximation? Well, we tried for non-Gaussian variables here. So for example, this is not a Gaussian variable, right? Here we've taken points from a bimodal distribution. The way I generated this one is that with probability 1/2 you are in this Gaussian, with probability 1/2 you are in this other Gaussian, and then there's noise, right? It's not Gaussian. And now I assume I take a measurement, which is very bad. Is this measurement, this line here, which says I know that the sample belongs to this line. Can I create samples of that original distribution conditioned to the fact that I have to stay on this line? Well, here you can see the difference. The black line is the correct probability distribution. You see there is a peak here when this crosses the first cloud, and there's another peak when it crosses the second cloud. And the histogram is the result of my projection. Okay? It's not exact, but it's better than other things. It's better than, for example, what we have seen in exercise 1, assuming everything is Gaussian and then computing the conditional probability, which is the red one. right? For example, this method gives you a bimodal distribution. If you at the beginning you said, oh, I mean, I assume everything is Gaussian, you will never get a bimodal distribution, for example, right? It also gives you finite support. If these points were in a finite support, by projecting them, they don't get scattered around, right? They stay in a finite support, which is something we like. Here is another example. Yeah, this is even worse. This is a very bad distribution. In 2D, these are points on this corona, right, on this annular distribution. And my measurement is that your point is on this black line here. What is the conditional distribution? Well, the exact one is easy. It's just 0 every time you're outside of the region. And then it's 0 point something. It's constant when you are inside the region. So it's these two things here. This is a very tricky distribution to compute conditional distribution for, right? And this is what you get. It's not too bad. There is a bit of concentration in the correct part and something in between. Is it good? Is it bad? Well, the important thing here is that the support remained limited, right? The support remained really constrained. And this is what will be the strength of this method. And if you see the first, second, third, and fourth moments of this distribution, we do much better than a Gaussian approximation. We do the same in mean and variance, but we do better in skewness and kurtosis. Skewness is whether it's symmetric or not, and kurtosis is whether it's pointy or flat. Okay? So you can look at these later. These are actually just illustrations of how accurate this conditional distribution is. Remember, that's the best we can do with linear operations. So it's not that we can do much better than this one. It's just to tell you that it's not exact. Okay? And now this is what I want to do in the third exercise, is you take your chance constraint optimization problem with a measurement, right? So there is a measurement here now. You convert it to scenario approach. So instead of probability, now you replace this one with samples from the conditional probability distribution. This is very difficult. We don't know how to do that. Then we apply third step. We replace this one with this transformation of the original points. Okay? And so what I claim is that if you can solve this one, which is literally really similar to what you've done already, but the samples are now have been transformed, then you actually get a good scenario or chance constraint solution for your solution with a measurement in the loop. Okay? Once you understand how you get there, implementing it is exactly the same thing. It's just that instead of the power demand, the sample, I have a transformation of the sample for which I need the y. And let me give you the quick, just a quick comment on one implementation aspect that you don't see in your code. It doesn't really matter, but it's good to know. So remember, we have just replaced the demand with these projected samples, right? So before we had the DI, and now we have this transformation of the DIs, okay? So what you could do in your code is to take all the samples, you have the measurements, you process them, so you have to take all your samples, compute expectation and covariance, compute K, you know what is H, you take your measurement, just make up a measurement of some kind, and you say, okay, with this information, I compute the projected samples, and then I solve the chance constraint optimization problem. Fine, this is exercise 3, right? You will have it in a second. The only tricky part, or interesting part, is that of all these elements, only this one is available in real time, right? This one, and this one, you knew it months before, right? There's nothing, this is the historical data. This is the only thing you have to do in real time. So natural question is whether you can do this operation, whether you can pre-process the samples already to be ready to do this operation, right? And that's something that you can try to do. I want you to know it's possible. It's not needed for your code, because in your code, it doesn't matter if you do it in real time or not. There's nothing real time. But I want you to know that you can separate the two options. So what you can do is that you construct a polytope. This was the original polytope, right? rg times g less or equal than all these quantities. And you remember, you construct this one, and then you can eliminate the redundant constraints and everything. You can actually construct a polytope where you also have the measurement as an unknown. So it's now a polytope in g and y. It's still low dimensional because g and y are small in number. And it's exactly the equation you have seen before, but now in matricial form. This is also a polytope. But it's a polytope not in G, which is what you had before, but in G and Y. Fine. This polytope, you can construct it months in advance. You have your historical data from the smart meter, you process them, you do whatever you want. In particular, you remove the redundant constraints there because you have time, and you're left with this polytope in a very compact representation. Now, once you do everything, once this polytope is ready, the only thing you have to do when you have the measurement is that you have now a polytope in G and Y, and you know Y. What happens to a polytope when you know that you have a value? Well, you have to, let me show you. You have to slice it, right? Because now it was a polytope in G, in D, and Y, and now you slice it because you know that Y is not any possible value, it's only here. And this slicing operation is trivially simple. So what you can do is that all this polytope is constructed beforehand, and you remove all the redundant constraints. That's what I mean by computational minimal representation. This takes you 1 hour. Okay, not now then. You go from 50,000 constraints to 12 constraints. And now in real time, when you have the measurement of the total demand for the substation, you only have to do this one and solve a QP, a linear program, on the intersection of the two. How long does it take to solve a linear program in 12 constraints? A millisecond, right? And this is mostly because it's MATLAB. Otherwise, it would be faster. Okay? So although this is not really part of the exercise, the nice part of this two-step thing where you construct a polytope and then you project is actually that you can have two phases. One is the offline phase where you construct the polytope. It's the augmented polytope based on the data. You have to work for 1 hour to construct it. You don't have to do it for the exercise, but you have an idea. And then in the online phase, you get your measurement, you slice the polytope, you get a decision. And so this part here, the white part here, is a 1 millisecond thing. And it's a 1 millisecond thing where the only data you need to store here and use, it's 12 constraints, right? So it's something you could have in your microcontroller, right? While the part here is something that the distribution system operator has to do when he has all the data from the last 6 months, process them, remove constraints, and so on and so forth. Okay. That's it, in the sense that the third exercise is really the same. You don't have to read it every time. It's the same things, but now there is one measurement, total power flow at the substation. And what you have to do is to say, okay, now you have this measurement. For this Y, assume that you can, for every measurement, of every sample, for every measurement, decide how much to curtail. So now the Gmax is not a Gmax for the entire history. It's a function of what you measure, right, of this Y, the total demand. And then you see what are the resulting voltages here, if it's better or worse than the one we did with the sans constraint. You will see the same thing as before, so it's exactly the same lines now, but now before you have to do a bit of, compute this K and so on. That's it, right? You verify again the voltage, the distribution of the voltages, and you see how much we have curtailed or how much we have generated this time. And then this question has a trivial answer. If you can do that, knowing this information allows you to curtail less, right? Because, for example, if you know that the total power demand of the entire plant was very low, then you know that you're close to the worst case, and so you have to curtail. But if you know that there is a lot of power demand at that moment that you're measuring, then you know that you can actually inject more power because a lot of power is going to be consumed locally. That's the intuition, right? And so, of course, if you have this measurement Y, you can improve, you can curtail less. If you don't have it, then you revert back to what you have seen. Okay, that's the third exercise, but that's also the end of the lecture. If you have set up the code properly for this one, trust me, once you do exercise 1, Number 2 and 3 are really just replacing this vector with slight perturbation of the same ideas. It won't take 3 times the time it's taken for exercise 1. I think they're waiting us for lunch. If you have some quick questions, I will be happy to answer now, or you can also talk to me over lunch.